So the bootstrap principle is if you have a statistic that estimates some population parameter that you're interested in, but you don't know that statistic's sampling distribution, then the bootstrap principle is simply to use the distribution defined by the observed data to investigate that sampling distribution, an estimate of that sampling distribution. The bootstrap principle actually doesn't require simulation, in the same way that if we want to know what's the distribution of the average of 50 die rolls, well, we could maybe mathematically figure that out. Good luck. But it's easier to do that with simulation. So we never kind of figure out what's the limit of what you get when you roll the die infinitely many times, because we can approximate that so well with Monte Carlo. We're also only going to cover a couple of aspects of what you can do with your bootstrap resamples. It's a rich subject, and we're mostly going to cover creating a confidence interval and estimating standard error. So we'll go over those two things. But let's go over the general procedure again. What you do is you take your observed data and you simulate complete data sets by drawing from the observed data with replacement. And this is approximately drawing, and for each of those simulated data sets you calculate the statistic of interest. And this is approximately drawing from the sampling distribution of that statistic, at least as far as the data approximates the real population distribution. So just as a reminder, we're going to calculate the statistic for each simulated data set, and then we're going to use these simulated statistics to either define a confidence interval or to take the standard deviation of this distribution in order to calculate a standard error.
So let's go through the bootstrap algorithm in a little bit of detail for calculating a confidence interval or bootstrap standard error for the median from a set of n observations. So the data that we have is a vector of length n. Then what we're going to do is resample n observations with replacement from the observed data to basically get a resampled complete data set. Remember, when you sample from the observed data, you're going to sample with replacement. If you didn't do it with replacement, then you would basically, after having sampled n of them, you would just have a copy of the data set again, just with the order permuted. Instead, it's important to sample with replacement, which means that you likely get some observations repeated on multiple times, which is fine. This is part of bootstrap resampling. When you get a resampled data set, in our example, we're going to take the median, or if you're using a different statistic, you'll simply take that statistic of the simulated data set. Then you're going to repeat this step over and over. I say b times here, where b is the number of bootstrap resamples. You want b to be large so that your Monte Carlo error is small. And what I mean by that is, remember, if we could, we would just figure out the exact bootstrap distribution without involving any resampling. We would just know exactly what the distribution of the median is from a distribution that places probability 1 over n on each observed data point. Instead, we're going to do it via Monte Carlo, this process of resampling, so you don't want the Monte Carlo error, or basically how long you've run your computer, to be driving your results. The easiest way to fix this is to simply make b be fairly large, 10,000 or more simulations. The medians that you get from this process are approximately drawn from the sampling distribution of the median of n observations. We're really sort of approximating the population distribution, but that's okay. There's a lot of theory that shows that the bootstrap actually works. When we do this, what we can do with our bootstrap resamples is, the first thing is you always want to draw a density estimate or a histogram of them. But you also could calculate their standard deviation, which will give you a standard error of the median, an estimated standard error of the median. You could take quantiles of your bootstrap resampled medians and say, for example, the 2.5th and 97.5th quantile, and those form a so-called bootstrap confidence interval for the median. So notice what we've done in this process is we've figured out a very easy way to develop a confidence interval for the median without having to do anything like fancy asymptotics. Let's go through some quick example code. Remember the father-son data, where our x is our son's heights. Remember we assigned this vector x to be the son's heights. I'm going to define b to be 10,000. That's going to be my number of bootstrap resamples. And I've already previously defined n as the length of x, the number of observations that I have. So if I want to draw n complete data sets with replacement, b complete data sets with replacement from x, then I need n times b draws. The R command sample does this, where it's x as the vector that I'm sampling from, n times b, the number of times that I want to draw from it, and replace equals true. In this case, if I didn't have replace equal true, it would give me an error because you can't draw n times b elements from x, which only has n elements, without replacement. This now gives me a vector of n times b samples from x. And now I'm going to simply arrange them into a matrix with b rows and n columns. So every row now is a bootstrap resample, and it has n observations. So I'm going to go along the rows in the next line and take the median for each row. When I take my standard deviation of my medians, I get 0.08473. This is an estimated standard error of the median. If we want a confidence interval for the median, I'm going to take my vector of resampled medians, and I'm going to simply take the quantiles, and I want a 95% interval, so I'm going to take the 2.5th and 97.5th quantiles. Gives a fairly tight confidence interval in this case because there's lots and lots of observed data. Here's my histogram of bootstrap resamples, and this is just always a good thing to do. I did it with ggplot, and so here you see me assigning g the output of the ggplot function. ggplot works on data frames, so I define a data frame as my collection of medians, and then my aesthetic, my x variable, is the medians. Then I'm going to add to my plot, I'm going to add a layer that is a histogram. The black means the bars, the outside of the bars are black. Fill being light blue means the inside of the bars I wanted to be light blue. And bin width talks about the width of the bins to create my histogram. Then I type G to actually show the plot. So this plot is an estimate of the sampling distribution of the median. If we had the true population distribution and we were to sample over and over again, this would be a very good estimate up to Monte Carlo error of the sampling distribution of the median. Instead, we don't have the exact population distribution. We've replaced it with the bootstrap principle of resampling from the observed data, and now instead we just get this approximate distribution of this approximate sampling distribution of the median. So a couple final notes on the bootstrap. The way in which we presented the bootstrap here is the so-called nonparametric bootstrap. The confidence interval that I showed you, just taking the 2.5th and 97.5th percentiles, is actually a somewhat poorly performing confidence interval, and you can improve on it very easily. The one I would recommend is called the bias corrected and accelerated interval, BCA interval, and it's very easy to implement in the bootstrap package in R. You simply take your bootstrap resamples and pass it through this function, and it just gives you the BCA interval. It's basically a quick little fix of what quantiles you take to correct for a bias. What I've done here is I've just given you a very basic introduction to the bootstrap. It is an incredibly useful procedure, and it has lots of variations and extremely wide applicability and a lot of intricacies when you try to apply it in settings like when you have time series, or when you have a regression model, or when you have longitudinal or multi-level data.